Resonance. Where you live. Resonance. We'll get the test packet in class. Have resonance, the gold sheet. Then you all have the diene, chemistry of dienes. I sent that to you. You should have that printed out. Chemistry of dienes. Okay, guys. Everybody doing okay today? Resonance. Question?
Are there any extra copies of this worksheet if you were like 6 days of class?
Extra credit, extra copies of what?
Copies.
Orange?
Yeah, orange.
Gold?
Gold.
You didn't get one?
Yeah.
Questions about resonance? Question? Do it. Do I need to give everybody another one? What happened to it? This is all I got. Pass those back, please. Any questions about resonance? Question? Uh-huh. Okay. Can't hear you.
I know what to go to. I didn't understand. It's under C. The second one under C.
Uh-huh.
I just want to see how it worked out. I didn't understand how
Two possible cations are reacting in alkene with H+. You're not going to react benzene in organic 1. Never react benzene in organic 1. Pi bond react with H+. We're either going to make cation there. I'm not going to do full mechanistically. Or there. That is new H there, cation there, or new H here, cation there. Which one you're going to make? Which one's a better cation? This one. Better cation. Why? It's resonance stabilized. You can draw resonance structures. Boom. Just like we did last time. Resonance stabilized cation. This is not. So this is going to be the preferred pathway. Why? Because the transition state leading to this is going to be lower. And then the I is going to attack here. And that's going to give that product there. So understanding carbocation stability by resonance will allow you to predict the regiochemistry. Questions?
Why don't we react benzene?
Do what?
Why don't we react benzene?
The pi electrons within the benzene are very stabilized by aromaticity. Typically, you do not destroy the aromaticity, and in general, we do not react benzene in organic 1. We'll do benzene reactions in organic 2. Okay, which carbons of the benzene ring of aniline are most electron rich? That would be this one, and this one. Those three are the three that are most electron rich. How do we do? Why is it those three? Because if you do a hybrid, you'll see those are the three that have partial minus charge, right? Due to resonance. Yeah? Yeah? Your resonance structures had minus on those three carbons? No. Your resonance structures are, you blend them all together to get the true structure. The three circled there. Any questions about that one? Which amine group of the two compounds above is the most electron rich? Top or bottom? Most electron rich. Who says bottom? Who says top? Who did not vote? The answer would be the top. It's electron rich. Why is that?
Because the top one you see, you can't really take a partial minus and put it on that oxygen, whereas on the bottom one you can do it.
Yes, that's it. We draw resonance structures of each one. We'll do that here. You have neutrals. When you have a lone pair, if that lone pair is in a p orbital, great place to start with resonance. That lone pair is in a p orbital. These electrons can move here. We can kick these out. Electrons in, electrons out. It's a plus charge. You kick these out. That's a minus. We didn't do anything with the other two pi bonds. And we didn't do anything with that. Electrons here, kick these out onto that carbon. During resonance structures of benzene type compounds, very important, we'll do it many more times in organic too. When we do benzene compounds, what does this arrow movement give? We didn't do anything here. We now have pi bond here. These electrons moved out here. It's going to be a minus. At this point, we can draw two resonance structures. We can move these in and move these out. That's a pi bond there. We're moving the pi bond out onto the carbon. That's a lone pair, that's a minus. That'll be A, that's going the A way. But here we can also move these out here and move these out onto the oxygen. And this will be the B way. We get a resonance structure that looks like that. Electrons moved out onto oxygen as a third lone pair. That's a minus. So 4 additional resonance structures. These electrons have been delocalized onto that carbon, that carbon, that carbon, and to that oxygen. Your resonance structures here, I'm going to ask you to do these on your own. You can only put the minus here, here, and here. This is going to be only 3 additional resonance structures. It's basically going to be the same 3 we drew here. This one we can move into the carbonyl because the carbonyl was there. Boom, out. Carbonyl is not on one of these carbons. We can never move the electrons into the carbonyl. 4 resonance structures, only 3 here. That means this lone pair is more delocalized than this compound. It's delocalized onto the carbonyl. That means the electrons are less there. They're moved all the way over even on the oxygen. These electrons are not delocalized as much. These electrons are not delocalized onto the oxygen. So which nitrogen has more electrons? Top one, the one in which the electrons are not delocalized onto the oxygen. It's more electron rich. This one's more delocalized. The more you start spreading the electrons around and moving into other atoms by resonance, let's take stock of the pi system here. How many p orbitals in the conjugated system here? It's sort of cross-conjugated, but how many here? If you line all the p orbitals up, how many would there be?
7.
9 p orbitals. 1, 6, 7, 8, 9. How many here?
7.
You see, it's cross-conjugated. Cross-conjugated gets into, it starts gray. We don't want to go there. It makes it look too similar. You have to get a deeper discussion. This is not good. It's cross-conjugated. Let's don't talk about that. That'll be more confusing than it's worth. More delocalization here. Okay, this is more electron rich. Because it's more electron rich, that nitrogen is going to be more basic. It's going to be more reactive as a nucleophile. It's going to do more things that electrons do. Act as base and act as nucleophile. This one's less basic, less reactive as a nucleophile on the nitrogen. Is there a question?
That was my question.
A delocalization of pi bonds to heteroatoms. This is neutral compounds. Again, up there they were neutral, but we have a lone pair that we could use in resonance, a lone pair that's in a p orbital. Here you have lone pairs. Are these in p orbitals?
No.
No, they're not. They're in hybrids. Okay, there's no lone pair in a p orbital. I don't know what's up with the board today. Pretty bad shape. A pi bond is known to be polarizable. I mean, if you have a sigma bond, you say it's polarized. Okay? You can say partial plus, partial minus. Same thing with a pi bond. But a pi bond is even more polarizable. The electrons can be pulled even more polarized to one side or affected by a heteroatom. Oxygen is more electronegative than carbon. We certainly have a dipole. But oxygen can pull these pi electrons so much that we can kind of just show them where the oxygen just pulled them up there. If you just move them up there, we'll go this way. Resonance arrow. Now the oxygen has 3 lone pairs. Now we have charge. The oxygen is minus, carbon is plus. So that's a polarized resonance structure of a pi bond that has a heteroatom. That's a natural tendency of the electrons moving towards the heteroatom. Now, on the other hand, you would never polarize them this way. You would never move them onto carbon. That would be a minus, and this would be a plus. That goes against the tendency of, or the electronegativity. Oxygen is not going to let the electrons go to carbon. The electron is going to move towards the oxygen. This is a bad way to move the electrons. Also, we said a golden rule that you never break with a heteroatom like oxygen, nitrogen, or halogen is you never leave them without an octet. See here, the oxygen does not have an octet. 2, 4, 6. Very bad. While it is strictly a resonance structure, because all we did was move pi electrons, it's a terrible resonance structure. So you can never show one like that. In the end, the electrons can be polarized towards the electronegative atom. Show all possible resonance structures for this guy here. Now, we said all possible. That doesn't mean show the terrible ones also. Don't show terrible ones. All the good ones. Okay, if you have any question about what's good and what's terrible, well, I've told you pretty much what's terrible. The terrible ones are the ones where the heteroatom has no octet. Never show those. How do you stabilize a cation? Move electrons away from it or towards it? Towards it. What electrons can you move towards it? Chlorine lone pair. Double bond to F. F now has positive charge. You can do a formal charge. All resonance structures have the same net charge. Any other resonance structures to show here?
Move the pi bond to the oxygen.
How many charges would you have to?
Positive and negative.
3. Yeah, usually what this will say is that involve delocalization of the cation. If I just polarize this up and show plus minus, that will not have delocalized the cation. So while that is a resonance structure, really we're trying to show resonance structures of the cation. I know the whole thing's a cation in it, but delocalization of the cation. A lot of times I see students want to do this. And a lot of times they'll end up with a third lone pair there. And maybe a minus charge. And there you go, that's a good one. No. Resonance structures have the same net charge. This has a certain number of valence electrons. All of a sudden, we got 2 more. I don't know where they came from. There ain't 2 there. Because there's 2 here. What does this mean? We're just moving the pi bond down. We didn't magically get another lone pair. Okay, what's the charge of this guy? It is positive. Okay, is this good resonance structure? No, no octet. No octet. Not good. Okay? Not good. If this was a carbon, if this was an alkene, it would be okay because carbon you can leave without an octet. That'd be a carbocation. But as a carbonyl, no. Of these 2 here, which one's major?
Second one.
This one here. Why?
This one's longer.
Because it has more bonds, even though the positive is on the most electronegative atom of all. Fluorine still has an octet. It's okay. This is major. If you can look at this cation, most of the positive charge would actually be on the fluorine. You could take a picture of the electron density. Effects on acidity. Hopefully you look back at the acid-base handout from the first test. Series of OH compounds. Regular alcohol has a pKa similar to water of about 16. Phenol, about 1,000,000 times more acidic. First of all, let's get rid of these H's. We want to consider the stability of the anion. Resonance stabilized. We drew resonance structures of the anion before. You can put the minus here, here, and here. Here, and here. 3 additional resonance structures. Stabilizes the minus, makes it more acidic, more willing to form. Phenol. Carboxylic acid is 1,000,000 times more acidic than phenols. Anion can be stabilized by resonance. Pi bond here. Move electrons out, so now there's 3 lone pairs there. That's a minus. 2 resonance structures. 2 resonance structures total. Here you can draw 4. A lot of students think because you can draw more resonance structures, it should be more stable, more acidic. No, because here the minus is on what? Oxygen, carbon, carbon, carbon. O, carbon, carbon, carbon. Here the minus is on what? Oxygen and oxygen. Turns out minus on oxygen and oxygen is way better than oxygen, carbon, carbon, carbon. Your carboxylic acid, your carboxylate, the charge is delocalized on the 2 different oxygens. That really stabilizes it. That's why it's so much more stable than putting it onto carbon. Delocalizing it onto carbon is better than no delocalization at all, but it's not as good as putting it on another oxygen. You should draw all resonance structures there, okay? These, we've already done that before. Does this make sense? Explaining that trend? You can look at phenols and start putting substituents on the ring and saying which phenol is more acidic. Now this is an NO2 group called a Nitro Group. Nitro groups we'll see in Organic 2. It was not on the functional group list for this course. Nitro groups are very common, especially in synthesis. Some drugs have nitros. Rohypnol has a nitro group. Let's see. It's more acidic. We really want to consider the minus, right? And we really want to ask, well, which minus is more delocalized? The more we can spread that minus around, the more it's going to be delocalized and destabilized. Nitro, okay, you should be able to put together a Lewis structure for it. But it's going to look like this. Double bond to O, single bond to O, and this O is actually going to be a minus. The nitrogen is a plus. So your nitro group has a plus and a minus there. It's net neutral. There's no way to draw it without charges. In one of these compounds, we can draw resonance structures of this. We can say it's moving into the nitro group. We can show a resonance structure of one of these lone pairs, and we can show a resonance structure with the charge actually over here, in addition to these charges. And one of these you cannot. You should do this on your own. But which one's going to be more acidic? The one where you can delocalize into the nitro group, or the one where you cannot? One where you can. You can move the minus into the nitro group. That's more delocalization, spreading the negative out, stabilizing it. And if the minus is more stabilized, that means it's more willing to form. And that's the definition of an acid. More willing to give up the H and becoming minus. You need to draw resonance structures and practice your resonance structures. Starting with the electrons here, electrons in, electrons out. And let me know if you have any questions. It's very common to have substituents on a benzene ring and to ask questions about them. How they affect things. Often boils down to resonance. Basicity. Which compound is more basic? Now give pKa's. Based on the pKa's, which one's more basic? Now the first one. More basic, less basic, not basic. Why is this one more basic than that one? Is this lone pair involved in resonance? And like we can delocalize it and show it moving on to the other out? No, no resonance. This is an isolated lone pair. What type of orbital is that lone pair in? And sp3. What type of orbital is this in? P orbital, right? Somebody said sp2? P orbital, right? Anytime a lone pair is next to a p orbital, want to be in a p orbital? Yes. Yeah, I mean, this p orbital's here all the way around. It's resonance. We can move electrons here and move these out. We've already done one pretty much like this, right? That would give plus and put minus here. Yeah? Yeah. I'm effectively saying that the lone pair is being put over here on carbon. So the electron density is being moved over here on carbon. The electron density is not just on that nitrogen. Here it is. But that one, the electron density is spread out. That's going to make it a lot less basic. Actually, if you look at the hybrid, that nitrogen has some partial positive charge on it, as seen in this resonance structure. So if we're talking about it being a base and reacting with H+, why would a partial nitrogen, partial plus, want to react with a plus? You see? Now, it does have some acidity. I mean, some basicity. That's kind of because the electrons are really not polarized this way a lot, because, see, carbon doesn't love being minus. While you can show such a resonance structure, the electrons just don't migrate this way. They sort of more stay here. So they're somewhat localized. But they're not as localized as this one. They're spread out a little bit here. How about over here? It's considered non-basic. If we draw a resonance structure here, go ahead, draw a resonance structure there that illustrates why it's non-basic. We're talking about the nitrogen. These electrons can move in here, and we can move these up. Now we have 3 lone pairs on the oxygens, a minus, and that is like this. So there's a resonance structure using the lone pair of the nitrogen to delocalize it onto the oxygen. Now here I said that the carbon, the electrons are not going to sort of migrate towards the carbon. What about here? Are they going to want to migrate towards that oxygen?
Yes.
Yes, oxygen is more electronegative than nitrogen. So this is a natural tendency of the electrons moving that way. We say it's sort of by resonance. So this is a pretty major resonance structure. I'm not going to call it the major one. This is probably major with everything neutral. But it's very significant, much more so than this one here going this way. So I'm going to say that electrons are more spread out here. And that's my explanation for why an ambit is considered non-basic. Nitrogen does not have a lot of electron density. And actually, the most electron-rich atom of the ambit is the oxygen, as seen by the resonance structure on the right. It's the one with the minus. High electron density on oxygen. Of course, the true structure of your ambit is something like this, with partial minus here and partial plus there, right? It's a blend of those. So where's your highest electron density? Right there, the minus, partial minus. You can answer questions by looking at our different resonance structures. Which nitrogen is most basic here? This is the same idea. We added a group. It's going to be the one that's delocalized less. The one that's delocalized into the group is going to be the least basic. Anybody have an answer here already?
Right.
Which one's most basic?
Right one.
It is the one on the right. Hopefully you have resonance structures and you can show that with your resonance structure. Do that if you have questions, let me know. In one of them you'll be able to draw 3 additional resonance structures. In the other one you'll be able to draw 4 additional resonance structures. The one with more delocalization is going to be less basic. Resonance of radicals. I'm not going to do that here. We may most likely cover some radical reactions again near the very end, and we will likely do resonance there. But you can do resonance of radicals. Radicals can be resonance stabilized. What does that mean? Essentially, you can have a pi system that has basically an odd number of electrons in it. If you show an isolated resonance structure, one atom is just going to have 1 electron. So please look back at the acid-base handout from week 1, where some resonance was covered. Resonance, of course, one of the fundamental building blocks of organic chemistry. The next 2 handouts, dienes and also mass spec. Understanding both of these will require you to use your knowledge of resonance. questions about resonance? Okay, I'm going to move to the chemistry of dienes. I know you've been dying to get to this handout. A diene. Diene has not one but two enes. Not one alkene but two alkenes. All right? So the compound at the top left up there could be called a diene because it has two alkenes, two enes. We saw this before. We saw conjugated and non-conjugated. What type of diene is that? Conjugated. The two alkenes are conjugated. Okay? We're going to react with HBr. We've reacted alkenes with HBr before, right? Cold and hot. We're going to have reactions that are temperature dependent. Different outcome. Diels-Alder reaction. Which drug looks like it can be made by a Diels-Alder? Okay, first thing, let's look at some nomenclature. We've already looked at A. A was on the previous handout. Nomenclature of your dienes, or really a polyene. Polyene would have two or more enes. They're all named by finding the longest continuous chain. So what is that for this guy? 1, 2, 3, 4, 5, 6, 7. It's your a heptane. If there's one alkene, we would call it heptene. But we see two alkenes. So we're going to call it a heptadiene. Heptadiene. Basically, you just are replacing the ane ending with diene. Guess what if there were three alkenes in there? It would be a heptadiene. Very good. Okay, heptadiene. But do we need any other information? I mean, what is this? 1, 2, 3, 4, 5, 6. What is that? It's also a heptadiene. What do we need? We need to say where the double bonds are at. You use the first number of the position, not both. The positions get the lowest possible numbers. We need two numbers here. What do you want to say? 2 and 4. 2, 4 heptadiene, because it's going to be 1, it's going to be 2, and that's going to be 4. First double bonds at the 2, 3 position, we just say 2. Next double bonds at the 4, 5 position, we just say 4. 2, 4 heptadiene. Okay, then what's the next one over there? That's also 2, 4 heptadiene, isn't it?
Yeah.
Okay, so this can't apply to two different structures, so this is ambiguous, not unambiguous. What do we need to clarify for this structure? What's the difference in these two?
One's cis, one's trans.
That's E, that's E, this is E, Z. This is E, comma E, and we'll put this in parentheses. Both double bonds are E. What's the other one? Z, comma E. I'm listing the 2 first and then the 4, and then it's the same name. They have the same basic name. They're both 2, 4 heptadienes. So there's what type? They're isomers, right? What type of isomers are they? They're stereoisomers. They only differ by some descriptor in the front. One is EE, the other is ZE. And yes, they're distereomers. Same name, they only differ by stereochemical descriptor, right? You could also have a ZZ, couldn't you? You should be able to also have a EZ, where the E is a 2 and the Z. So there should be 4, right? Because there's 2 stereogenic alkenes. 2 to 2 is 4. Okay. What do you want to name this guy over here? Both alkenes need to be in your longest chain. 1, 2, 3, 4, 5, 6. That's it. 1, 2, 3, 4, 5. Even if this was this long, it doesn't matter. You got to have the other one in there. So right across here, 1, 2, 3, 4, 5, 6. Hexadiene. What do you want to call it? 1,5 hexadiene. What's on it? 1 chloro. 2 purple. 1,5 hexadiene.
No, only one of them stayed one.
Good. We need to put, what do we need to put in front of this? E.
You know which one that E refers to?
The one that it refers to. Which one does it refer to?
I mean, the one that's
The
listed.
stereogenic one.
Yeah.
Which one's stereogenic?
I guess, can you deduce that from the name?
Yeah.
Okay.
I mean, the other one is not relevant. That's how. There's only one where it's relevant, right? So you don't need to put a number. If you got 2 of them, they're usually listed in terms of numbering. I mean, this is the first one, the 2, that's the 4. I reckon you may see it 2E, 4E or something. But to me, you don't really need it. This must be the first one, the second one in terms of number. It's E. I mean, this is E. That's not stereogenic. You don't need any stereochemical descriptor there. How's the name look? Okay. Okay. Brief comment on terpenes. Y'all heard of terpenes? Terpene is a diene, 5-carbon diene right here. Okay. 1,3-butadiene, 2-methylbutadiene. 1,3-butadiene. I reckon it could be accumulated. This is one of nature's building blocks. Lots of natural products are made from this monomer, C5H8. Limonene, it's in lemon. Is a dimer. C10H16 is a dimer. And the 2 of these react together. You ever seen two things react together? Does 2 alkenes react together? Yeah. Okay. Acid catalyzed. You could do a mechanism for this. There's lots of more, even more sophisticated natural products that come from isoprene are called terpenes. They could be C10. These all have multiples of 5. Taxodiene is probably not heard of. Retinol you've heard of. C20. Now this is not an exact multiple of C5H8. It should be C20H32. Okay? So it's not 2032. It's a little bit of change that happened along the way. So it's not a true terpene. Instead, it's a terpenoid, terpene-like. It's not an exact multiple. So retinol is a terpenoid. Then you have others. Squalene. A lot of these are found in like fungi and beta-carotene. Usually you see multiples of 5 in your carbons, so that's 40. So what's that? Times 8. 8 times 8 is 56. Hey, that's an exact multiple. Looks like it. Looks like beta-carotene is an exact terpene. You also recognize terpenes because they often have 2 methyls on like 1 carbon. Methyls. You get that from sort of the 2 methyls on 1 carbon of the original. You can read below a little bit. So that's just more of a sort of a little miscellaneous application, just a term that you need to be familiar with, so you don't go out there and say, I've never heard of terpene. No. No, you haven't.
Is turpentine related to terpene?
Turpentine, you know, I don't know the structure of turpentine,
Okay.
but very likely it is. A lot of those come from like natural products and like the pine trees and stuff. It probably, if you look at the structure, it's going to look like terpene or terpenoid. You'll probably see some dimethyls. Yeah.
So what's
Isoprene is the original C5 mono.
Oh,
I may have called it terpene at the beginning, but that's isoprene.
so that's just
Yeah, this is isoprene. And then it can start dimerizing and you build up. And nature is an amazing chemist.
Yeah.
Mother Nature's bad mama gem. All these compounds. Okay, let's try some reactions and see if we can do like Mama Nature. If you take, hey, is that isoprene? I think it might be. If you react this with HCl, did I skip a page?
Yeah.
Yeah, it looked like it. I'm thinking to myself, how did we get here? Do I not have the, am I missing a page? I'm missing a page. Do I? Yeah. How did I get a missed page? D. No, I'm missing a page. No, nobody's got an extra. You got an extra? I don't have an extra.
Dr. Stevens, you can just use mine.
Do I? Well, sorry about that. I don't know what happened with that one. Okay, 1-2 addition. Also going to be called direct addition. We're adding, doing addition reactions to conjugated dienes. How do we get that product there? Well, we got H plus and Br minus. We can show it ionized or you can do it covalently. But it's not both. These electrons attack H plus. We then get UH added here. We're gonna make cation on left or right? Correct, on the right. Why? It's secondary. But in addition to it being secondary, what else is it? It's also resonance stabilized. Yeah? Okay? Now if you reacted over here, that's a symmetrical dying. We would have gotten the same outcome. It would have just been flipped around on you. They're resonance stabilized. By the way, which one's major of the two? Are they equal or is one better than the other?
First one less better.
Secondary, primary, it's got character of both. But which one does it look more like?
First one.
It's more like this one. How do we get final product? Br minus adds here. Get that product, right? To get that product, we didn't even have to consider resonance. You just make cation and add Br. Boom. This is called a direct addition. What we did 2 or 3 weeks ago was direct additions. If you look at, where's the new H at? Right there? Because originally there's 2 on the end, now there's 3 on the end. If you look at the position of the H and the Br, if we call that, let's call it 1. How about that? If that's 1, what's the next carbon? 2. Okay? The H is on the 1, the bromine's on the 2. That's why it's called a 1-2 addition. That's where you added the atoms, 1 and 2. It's also called a direct addition. Once we do something else, you'll be able to compare what these terms mean. This is the outcome if we do this at cold temperature, minus 78. That's the temperature of acetone and dry ice. That's why it's minus 78, not minus 72. It's just very convenient to achieve this temperature. Very cold, don't stick your finger in it. You get this product. This is called the kinetic product. It's formed fastest and thus first. Why? Thank you. Why we'll have to answer it a little bit later. Once we do below. We need to know why it's formed fastest and first. Okay? That's just what we did 3 weeks ago, except we did show resonance over our cation, right? Okay. And down below, if you do this same reaction but do it at a higher temperature, like 40 degrees or higher, you actually get this other product. Now we've added HBr to this because if you do formula, we now have HBr added. Where's the new H? New H is here. Because there's 2 on the end there, but now there's 3. So that's 1. Where did the bromine end up at? Not next door, so it's not 2. Not there, it's not 3. It's where? 4. So the H is at the 1 and the bromine's at the 4. This is called a 1,4 addition. Now here we didn't directly add the HBr to the alkene. We did something kind of odd. Question?
Do we start counting where the new H is added, and then you just count down the line?
Or you can count where the bromine is at and count the other way.
Okay.
The relative relationship is 1 is at the 1, 1 is at the 4. Either way you want to go. It's like you live there and your neighbor lives not 2 houses down, but 3 houses down.
Okay.
Either way you want to go, it's a 1-4 relationship. This is going to be called a conjugate addition. We'll say why. This is going to be the thermodynamic product. It's the most stable. Compared to above, we can answer why. Why is this product more stable than the one above? It's all based on the alkene. The alkene above has 1 carbon substituent. The one down below has 2. Which one's more stable? 2. They're isomers, But this has 2 carbon substituents. We learned that, what, a month ago? More carbon substituent, more stable. This is more stable. So we call it the thermodynamic product. The thermodynamic product is your more stable product. But it's not formed fastest. Which one's formed fastest? The one above. The least stable is formed fastest. And the one that's formed fastest, what do we call it? The kinetic product. Now we're snowballing. Question? You had a question?
I was going to ask something about Nitro Group.
Question?
You have like a temperature in between. How do you know which one will form? It's directly in the middle.
Research.
Oh.
I don't know what the temperature cutoff is. You might get mixtures. Okay, let's do mechanism here. Well, really, I could have just kept the one above. Question?
So are the kinetic product and the thermodynamic product ever be the same thing?
They could be the same thing. Question?
Why is, if that one's more unstable, why is it faster?
We're going to look at that with a reaction coordinate diagram on the next page. Hopefully it's on the next page. Question?
Once you made a product through heating, can you convert it to the other one or no? Because it's already been done.
You can convert these back and forth.
Okay.
But if you establish an equilibrium, your thermodynamics will be favored.
Okay.
Yes. Let's answer some of these questions. Mechanistically, I wish I hadn't erased because we were already set up to make this product mechanistically. I'm just going to redo what I had up there. First step, really doesn't matter which alkene, it's symmetrical outcome. H plus, this here, where we're going to make cation. Cation there, right? What did we do before? We showed resonance. We showed resonance, what do you get? Get that cation, right? Windshield wiper over. Cation on the end. How do you get final product? Br minus adds there. That gives that product. If you add Br here, you get the 1,2 product, right? If you add Br here, you get the 1,4 product. Okay? Now what are these? Resonance structures. What's the true structure look like? The true structure looks like the hybrid. It looks like, let's see, partial bond, partial plus, partial plus. As soon as this happens, this is what you get. But instead of showing this with this partial stuff, which gets kind of cumbersome, what do we show instead? We show the 2 fake structures. We call them resonance structures. They're easy to work with. But you got to remember, this is what you get. So what you get is, you got a pi system where 2 different carbons have partial plus. And that Br minus then has a choice. Well, I could add here, because minuses like pluses. So we got a partial plus and we got electrons. Can you see some attraction there? Or it could wander over here and attack over there. You add here, you get the 1,2 product, which you get if it's cold. You also get this product first. If it's warm, you get this one. The bromine ends up adding here. Okay, why is this the fastest product?
Closer.
Very good. Why is the Br over here? I drew it over here for a reason. Where's the Br at this point? Pretty close to the plus. Even though these are ions and they're separated, aren't they still kind of close together? So the Br minus is probably close to the H plus. The H plus is over here, the Br minus is sort of over here. Once all this forms, Which one is this going to bond to fastest? The carbon that's right there, or the one that's across the country? Boom, that's faster, closer, proximity effect. Okay, it's faster. Just because the bromine is nearer to that carbon. That's why that one's faster. But is that the most stable product? Is that the most stable product up there? No, that's not the most stable product. The most stable product requires kind of a cross-country trek to get over there. Now, if we put that in chemical terms, which one's going to have higher activation energy? Boom or traveling across country? Which one's easier? Boom or going across country? This is easier. I mean, that's why it's faster, because it's easier. But it doesn't lead to the more stable product. Let's turn the page and let's look at what hopefully is going to be a reaction toward the diagram. Is that what's next? Is that? Yeah, right? Y'all got this right? Here's the reaction we're looking at. Okay? This is just drawn out instead of line bond, it's sort of partially condensed formula structure. Same reaction. Either way you go, you get the same intermediate. And this intermediate is a resonance, there it is right there. So it's a hybrid. Okay? From there is where you get the difference. Over here, two products. Which one's more stable? 1,4. That's why it's lower. There's the 1,2. Okay? 1,2 is not as stable. Okay? Which one is the easiest activation energy to attack?
1.
Closest one. Boom. That's easy. If I have to walk way over here, that's going to take a lot more activation energy. So, you see how the 1,2 has a lower activation energy? But it leads to the less stable product. Now, if you do it cold temperature, you never have enough heat to get up there and do the activation energy for the 1,4. If you do it cold, you can only go the small route and you have to just be here. And you never can go backwards and get over that big hump. To get over that hump, it requires heat. So there's your cold product. Why then, if we do it hot, do we get the 1,4 product? Larry?
I'm assuming that the 40 degrees Celsius was established by experimentation.
Yeah. Yeah.
Room temperature is pretty close to that, much closer to that than the -78 degrees Celsius.
It's probably at room temperature you may get mixtures.
So it's not binary then, one or the other.
Yeah, it's probably mixtures in between. We're looking at the two extreme ends.
Okay.
It could be, you could end up with a mixture. Typically this is very cold temperature, your major product is the 1,2 product. But if you start heating it, your major product is going to be the more stable, supported. With heat, see, heat allows you to reach equilibrium. What would that mean? Equilibrium. That is, how do you go from here to here? If you were here, how would you go to here? Can you just do that? No, you got to go all the way back up to the intermediate. That actually is the bromine leaving. Okay, and we'll do that a little bit later. But then you got to go over that hump. You can only do that if you have enough heat. But if you got plenty of heat, you can go back and go over. Then you can start doing this, going back and forth. At that point, you've reached equilibrium. And if you can reach an equilibrium where you're going back and forth, then what becomes favored? The more stable one becomes favored if you can reach equilibrium. And if you reach equilibrium, this is now the favorite. You can only reach equilibrium with enough heat to get you over the second hump. If you keep it cold, you'll never go over the second hump. Think about it. Faster here because of proximity effect. But the 1,4 is more stable because disubstitute is more stable than monosubstitute. Let's put this to use. Think about that. See if you have any questions. Let's try some. Okay. Now we're going to start looking at non-symmetrical dienes. This alkene has a methyl, that one does not. Now we have to decide which alkene are we going to react. Here's the way the reaction is going to go. You want to form the best cation intermediate. The best cation intermediate. Now, first off, you always want to make the cation in the middle because you always want it to be resonance stabilized. You always want your cation to be resonance stabilized. If possible, right? It's going to be better. To be resonance stabilized, it's going to have to form in the middle. Let's react here. If this reacts with H+, cation in the middle. Of course we'd put it in the middle there, wouldn't we? We could do that without even being told that. Here. Then we can do resonance. So this is a resonance stabilized cation. It looks like that. Now I could show the hybrid, but I'm not going to take time to do that. I'm going to instead ask this. The hybrid has characteristics of both of these. It has secondary cation characteristics and it has primary cation characteristics. Let's react the other alkene. That would give UH there plus here. Electrons hinging out plus here. Resonance stabilized cation. So they're both resonance stabilized cations. Is that right? But this one has tertiary and primary characteristics. Which one's better, tertiary primary or secondary primary? Tertiary primary. This is your better cation. So that's the one that's going to form. At this point, get rid of all this. Okay? So the alkene we're going to react with is the one on the right. Now, we have two cations. Cl is going to end up adding to which one? Cold temperature. Which product are we going to get? In terms of 1,2 or 1,4? 1,2. So that means, which one do we add the chlorine to? Here. Chlorine adds here. H is here. Chlorine is 1,2. Which one is that up there? Yeah, that one right there. Isn't that it? I mean, where's the new H in? On the end? Okay, 1,2 product. Now there's another 1,2 product up here, but it's not the right one. Where's the other 1,2 product? Yeah, see that's also a 1,2 product, but that's where it did a direct addition to that pi bond. We already said that's not the best cation. We're doing a direct addition to this pi bond, which is also a 1,2 product. There's your product there at full temperature. Question?
This being exemplified
This is an example of cold temperature always preferring 1,2 product. Cold temperature 1,2 product, right? That's it. Cold temperature 1,2. Right? Look on previous page. Cold temperature, which one's favored? 1,2. With heat, which one's favored? There's where you got to be careful. With heat, what's favored? The most stable is favored with heat. In my original example, the 1,4 was the most stable. 1,4 is not always the most stable. That's where your jumping to conclusions can hurt you. 1,2. Cold temperature 1,2 is always favored. Proximity effect. With heat, the most stable is always favored. Not always 1,4. Question?
So is this an example of when cold temperature and hot temperature produce the same product?
No, you want to do this hot. If you do this hot, which product would be favored?
The alkene is more substituted on the second.
If you heat it, the second product is going to be favored. But it comes from chlorine adding here. Right? Here's your two possible products from your cation. This is one cation, right? Okay, of the two, which one's more stable?
Right.
Well, the right. That's what you get with heat, right? With heat, that would be the favorite product. And it is indeed a 1,4.
And that's because it's the most substituted, right?
Yes, most substitute. It's got 3 carbon substituents. This one only has 1 carbon substituent. Question? How would you get the fourth one? You're not going to get the third or fourth from this reaction. Remember the cation I marked out? It's not going to go there. It's not going to form the worst cation. Okay. Reactions below. You do these on your own? Any particular one you want to do right now? You don't want to do one right now?
Was the one in the HBR?
We do the one with the HBR?
Like the one at the bottom on
All right. On the, this one? We'll do that one there. Okay. Which pi bonds are we going to consider?
Top one.
How about the benzene ring?
No. We don't do that.
Not an organic one? Okay, good. Don't do it here. You got your diene up here. That's not considered a triene. That's considered an aromatic benzene ring. Right here. We have to go through the cations. If we do cation up here, you can only plus on left or right. Correct. UH here, plus there. I'm just going to call that phenyl. Why plus there? Well, it's tertiary, but that's not the main reason. The main reason it's resonance stabilized. So let's draw the resonance structure. Plus there. Is that the resonance structure? Okay, we're heating this, so which product's going to be formed? The most stable. Is the most stable going to be the bromine bonded here or the bromine bonded there?
No, the lab.
It's going to be here. Because I'm going to go ahead and do it. Bam. This is an alkene over here. How many carbon substituents? 1, 2, 3, 4. Tetrasubstituted. It's going to be more stable. If you put bromine here, that would be only trisubstituted. There you go. Heat's most. Hold on.
What did you want
No.
to break the other?
No, we didn't do something. I'm trying to rush it, and that's not right. What did we not do?
Break, what you want to break the other alkene?
Yeah. Yeah. Yeah, that's not right. We didn't consider the other alkene. We did not consider the other alkene. We got to consider the other alkene. If we react here, where are we going to leave cation, left or right?
Right.
Correct. So we get new H there. Cation here. Yeah, I really jumped the gun on that one. We're out of time, but let me do this, guys. Electrons down. Here, cation there, UH there, benzene ring here. Here's resonance. Methyl. The original cation we had tertiary and secondary. This cation, it's a hybrid of this, right? It's only one cation. It's what? Tertiary. What's this? Secondary. But is it? They both look like tertiary secondary, but one of them is better. Which one's better?
One that's
Not only is this tertiary, but it's also what? It's also resonance from the benzene ring. We got resonance here from the benzene ring. That's a benzylic cation. That's going to be your better cation. Tertiary with resonance is better than tertiary without. There's no resonance here other than what we showed. Of course, that has the resonance from that pi bond also. Additional resonance. This is going to be favored. I really jumped the gun. So with heat, we get the most stable. Which one's going to be most stable? Bromine or bromine here or there? Going to add bromine here. Bromine added here. Double bond is tetrasubstituted. If we had added it here, the double bond would have only been trisubstituted. That's actually a product of heat, not this one. Because the cation that you get is that cation. You got to first choose which cation. There's others to work. I included the answers to these in the handout. They're on the next page, upside down. Don't look at them unless you want to. We'll see what kind of questions we have next time about these. We'll look at Diels-Alder next time, and we'll also begin mass spec. Please be reading about mass spec.